Hello everyone, you're welcome to my YouTube channel, and if this is your first time coming to my channel, I would advise you hit the subscription button so as to encourage me to make more videos. At subsequent times, I'm going to be releasing videos on civil engineering problems like theory of structures and mathematics as well. But for today, we are going to be talking about three moment equations. And as you can see, we have a problem, a beam with three supports. The first support is a fixed support, the support B is a roller support, and support C is a fixed support. And we have a load of 50 kilonewton acting on the mid span from B to C. And then from A to B, we have a uniformly distributed load at 50 kilonewton per meter. So we are trying to resolve this problem, and then we'll draw the bending moment and shear force diagram at the end of the video. So to solve this, we have a settlement. If you notice very well, we have a settlement at span A and we have a settlement at span B. The settlement at span A was 20 millimeters and at B is 50 millimeters. Since our EI was in meter square, we need to convert, our unit here is in meter, so we need to convert the millimeters to meter. Doing that, we just need to divide it by 1000, and dividing 20 mm by 1000 will give us 0.02 meters. The same way, if we divide our change at B, our settlement at B, which is 50 millimeters, dividing it by 1000, we give our answer at 0.05 meters. So the very first thing the next thing we are going to be doing here is to load our beam and also to transpose the beam. So if you are loading this beam, I'm assuming that this is the beam. Sorry, I'm using a freehand sketch. This is the beam at point A, we have here at point B, and here at point C. So if I should load this beam, my loading is going to go a parabolic shape, just like we know the bending moment of a UDL normally form a parabolic shape. And if I should load the same thing for this span, I'm going to be forming a triangular shape. Then I need to transpose this load. Transposing the load, this is my beam, transpose it to move upwards, and then this forms this, where this is my maximum bending moment and this is my maximum bending moment. To calculate this, we know that our maximum bending moment which should be the height of any shape we are calculating. A maximum bending moment for A to B, since it is a parabolic shape, we'll have it as WL squared all over 12, where our W will be the load, which is 50 kilonewton, our LU will be the length of A to B. So if I should substitute, I'll be having 50 times 6 squared all divided by 12. And for here, I'll be having my reaction at A left, and I'll be having my reaction at A right. This is the right hand side of A, and this is the left hand side of A. So at the left, the same way here, at the left hand side of A, I'll be having my reaction at B left, and at the right hand side of A, I'll be having my reaction at B right. And here, I'll be having my reaction at C left, and my reaction at C right. Why I am having at C and at B, even though there is no load here, but because it is a fixed support, I need to introduce an imaginary reaction to this, and also need to introduce an imaginary reaction to this and call it my C prime, call here my A prime. Normally, if this was not a fixed support, you wouldn't need to be introducing any imaginary length to it, but because it is a fixed, that was why I had to introduce an imaginary length to it. So for this span, let's continue from our maximum bending moment. We calculated the maximum bending moment of A to B as this, and then the maximum bending moment of B to C Since it is a triangular shape, we'll have it as W. Since it is a point load, rather, since it's a point load, we have it as WL over 4, where our W will be the load acting on that span, which is still 50 times the length of here to here, gave me 6 squared, all divided by 4. So this would turn out to be 50 times 6 squared divided by 12 will give me 150 kilonewton per meter. Then 50 times 6 squared divided by 4, my answer here is 450 kilonewton per meter. So since I have this value of calculated this, that means I can comfortably calculate my imaginary reaction, which is the next thing I'm supposed to do. So to calculate my imaginary reactions, we'll calculate our reaction. Because this is a UDL and the load is uniformly distributed and it's carrying the same span, that means that my reaction at A right will be equal to my reaction at B left. So doing that, I'll have that my reaction at A right will be equal to my reaction at B left. And the formula we use to calculate our imaginary reactions are area times the centroid, all divided by the length of A to B. And then if I should substitute, we know that an area of a parabola, it's always 2 divided by 3 in brackets, the base times the height. Then the centroid of a parabolic shape is the length divided by 2, and at this point we are referring to the length of A to B, so I have to include that the length of A to B divided by 2, then everything was all divided by the length of A to B. Substituting inside this formula, I'll have that this is 2 over 3 in brackets, the base here is 6 times the height is 50, then multiplied by the length, which is still 6 divided by 2. Length of A to, don't get confused, the length of A to B is 6, and then I'm dividing it by 2, all divided by the length of A to B, which at our question was given to us as 6. So if you calculate this, we would have this, that this will be 2 over 3 multiplied by 6 times 50 divided by 2 divided by 3 times 6 times 50 multiplied by 3, all divided by 6. Answer here is 100 kilonewton. Because it is reaction I'm finding, that is my unit. That is why my unit was in kilonewton. So the next thing I have to do here is to calculate my reaction at B right. My reaction at B right, the same way, is going to be equal to my reaction at C left. Why? Because the load is acting on the center. So whatever thing that is going to be happening here, it will still be the same thing that will happen here. So if I should calculate my reaction, but if this load was not acting on the center, we would treat a question like that in my next videos, and I will be able to explain that. But for this particular problem, it is acting on the center, and because it is acting on the center, the reaction at B right will be equal to the reaction at C left. Sorry, if you have any questions to ask, you can just drop your questions on the comment box and I'll reply to you. So if we should continue, we have that our reaction at B right to be equal to our reaction at C left, and we should still carry the same formula, which is the area multiplied by the centroid divided by LO, the length of B to C. And the area of a triangle that we know is 1 over 2 multiplied by the base times the height, and the centroid of a triangle is the length divided by 2. And here we are referring to the length of B to C, so I'll include the length of B to C divided by 2, all divided by the length of B to C. And if I am to substitute inside this formula, this is 1 over 2 and brackets, the base here, the B here is the length, which is the length from B to C, and the length of B to C was 6 times the height. The height in our question was 450, so we have here as 450. Sorry, the height in our question was 450, all divided by 6 divided by 2, all over LBC give us 6 meters. So if we should calculate this, we'll be having that 1 over 2 times 6 times 450 times 3 divided by 6, giving me 675 kilonewton. So for this, I noticed that we use 50. We are supposed to have used our height as 150. Remember that we are referring to the length of A to B, so the height here would be 150, which should have been this. So to resolve this, to calculate the height of a parabolic shape, we should have used this formula, which was 150. That means we've calculated it and we had 150, and the maximum height here was 450. So to resolve this, we have 2 over 3 times 6 times 150 times 3 divided by 6. This will give us 300 kilonewtons. Sorry for the mistake. So if we should continue, I've been able to calculate my reaction at A right and my reaction at B left, my reaction at B right and my reaction at C left. So the next thing I have to do here, already we know that this is an imaginary length, so there's no length I gave to it. So definitely my reaction at C right to be equal to 0 and my reaction at A left to be equal to 0. So I won't need to calculate that, or you can include it here that your reaction at A left is equal to your reaction at C right, and everything will give you 0 kilonewton. So the next thing I have to do after calculating your imaginary reactions is to calculate your settlements. And at this point, I am going to be calculating my settlement at the support that I need. At this point, I have a settlement. I have settlement at A and I have settlement at B. So I am going to be calculating my settlement at A. To calculate my settlement at A, we use a formula minus in brackets the settlement at A minus the settlement at A prime. That is the settlement at A minus the settlement at A prime, which we already know that settlement at A prime, there is no settlement at A prime, so when we are substituting, we have that value as 0. So the settlement at A minus the settlement at A prime, all divided by the length of A prime to A, then plus the settlement at A minus the settlement at B, all divided by the length of A to B. So substituting inside this formula, we are going to have this as this is minus in bracket. My settlement at A was 0.02 minus, I don't have any settlement at A prime, so I'll have it as 0, divided by the length of A prime to A is still 0 because there is no length at A prime, so I have it as 0. Then plus the settlement at A 0.02 minus the settlement at B was 0.05, all divided by the length of A to B, which the length of A to B is 6. So resolving this, I have this, everything here will turn to 0. Then the other side 0.02 minus 0.05 divided by 6, that will give me minus in bracket minus 0.005, and minus times minus will turn to 0.005. Likewise, the same thing, we are going to calculate our settlement at B, and our settlement at B will now be equal to minus in bracket. The same way we did this, we are going to be taking, when we calculated the settlement at A, we took these supports 1, 2, 3. Now when I'm referring to settlement at B, I am at B, so my formula is going to be my settlement at B minus the settlement at A, all divided by the length of A to B. Then likewise plus the settlement at B minus the settlement at C, all divided by the length of B to C. Don't get confused. You don't need to cram whatever formula. Every formula can be generated right there as you're solving your problems. So if I substitute inside this formula, I'm going to be having that this is minus in bracket, settlement at B was 0.05 minus 0.02, all divided by the length of A to B was 6, then plus settlement at B 0.05 minus, there is no settlement at C, so I'll have it as 0, divided by the length of B to C was still 6 meters. So if you should resolve this, you are having that 0.05 minus 0.02 divided by 6, I'm having minus in bracket 0.005 plus 0.05 divided by 6 would give me 0.0083. So if I should add this with my last answer, which is 0.005, will be equal to minus 0.013. So this is my settlement at A and this is my settlement at B. Remember, we are going to be taking this because this is a fixed support. I added an imaginary length to this. Likewise, the same thing, I'll add an imaginary length to this side. So when I'm generating my equations for slope deflection, I'm taking the first three span 1, 2, 3, the next one 1, 2, 3, and then the next one 1, 2, 3. So because I am taking my at support A, I'm going to be generating an equation. At support B, I'm going to be generating an equation, and at support C, I'm also going to generate an equation. So for those supports, I'm going to be calculating their settlements as well. I've calculated the settlement at A to give me the settlement at B to give us this. Likewise, we need to calculate our settlement at C. The same way, my settlement at C is still going to be minus in bracket the settlement at C minus the settlement at B, all divided by the length of B to C, then plus the settlement at C minus the settlement at B. The settlement at C minus the settlement at C prime, all divided by the length of C to C prime, which if I should substitute inside this, I'm going to have that this is equal to minus in bracket the settlement at C was 0 minus the settlement at B was 0.05, all divided by the length at 6, then plus the settlement at C minus, there is no length between C to C prime, so everything here automatically tends to 0. Then I'm only having this, so 0 minus 0.05 divided by 6 would give me equal to minus 0.0083. So this is my settlement. So the next thing I have to do here is to generate my 3-moment equations. And to generate my 3-moment equations, I'm going to have it that at support A, I'm only generating my my 3-moment equation at supports that I know that there is going to be moments. At A, I'm going to definitely have a moment because a fixed support has moment. At B, it is a roller support. It's not supposed to have moment, but for the fact that it's in the mid-span of a beam, there would be a moment. Though at the end of everything, when I sum up my moments there, I'll still have it as 0. So but then at C as well, I'm going to have moments. So that is the reason I'll be generating my 3-moment equations at support A, support B, and support C. So at support A, we have our 3-moment equations as M A prime multiplied by the length of A prime to A, then plus the 2 moments at A multiplied by the length of A prime to A, then plus length of A to B, length of A prime to A and A to B, then plus the moments at B multiplied by the length of A to B, which should be equal to minus 6. The reaction at, since I am at A, I'm going to be using my reaction at A left and my reaction at A right. So the reaction at A left, I naught over I, minus 6, the reaction at A right, I naught over I, then plus the 6 multiplied by the Young modulus multiplied by the settlements at A. But at this instance, our reaction at A left was equal to 0. Remember, from where we did this, our reaction at A left was equal to 0. So the same way here, my reaction at A left, since it is 0, everything here would definitely cancel out. So my length at A prime to A, there was no length at A prime to A. So my length at A prime to A would also cancel out to be 0. My moment at A prime would be 0 because there is no moment here. There will be no moment there, so I'll cancel it out to be 0. So for the remaining part of the equations, I'll have to be substituting. Then the next thing I have to do here is 2 moments at A multiplied by the length of A to B. The length of A to B was 6. Then plus, I don't know the moment at B, so I included moment at B multiplied by the length of A to B, which was still 6, which is equal to minus 6 in bracket the reaction at A right. The reaction at A right, we calculated it as 300 kilonewton. So I have to include it here as 300 kilonewton. My I naught over I wasn't given to me, so I wouldn't be using that. So the next thing I have to do here is plus 6 in brackets. My EI on the question was given to us as 3,000, remember. So we include that as 3,000 multiplied by the settlement at A was 0.005. So resolving this, 6 times 2 will give me 12 moments at A plus 6 moments at B, and everything here is going to be giving me minus 6 as minus 6 times 3,000, minus 6 times 300 plus 6 times 3,000 times 0.005. So my answer is minus 1,710. Then, or I can further reduce this my equation by dividing everything by 6. If I decide to divide everything by 6, if I divide here by 6, I'm going to be having that 2 moment at A plus moment at B would be equal to 1710 divided by 6. So this is minus 285. So I will call this my equation 1. We're almost close to our answer. The next thing I will do is to calculate or generate my 3-moment equation at support B. Generating my 3-moment equation at support B. Here I've taken the first 3 span, which is A prime, A and B. The next span I'm going to be taking is A, B and C. And at A, B and C, if I'm taking that span, my 3-moment equation will now turn to be moment at A. I always start from the first support of the span I am generating my equation. So this will be moment at A multiplied by the length of A to B, then plus 2 moments at B multiplied by the length of AB plus the length of BC, then multiplied by the moment at C times the length of B to C, then equal to minus 6. I am at reaction B, so I'll be using my reaction at B left, I naught over I, minus 6 reaction at B right, I naught over I, plus 6 multiplied by the Young modulus times the change at B. So when I substitute inside this formula, my moment at A will be existing, so I need to find that, and the length of AB was 6. From my question, the length of AB is 6, so I have 6 MA plus 2 moment at B multiplied by the length of AB is 6 plus the length of BC is still 6. So I have this plus moment at C multiplied by the length of B to C, which is 6. then equal to minus 6 in bracket. The reaction at B left from our initial calculation, the reaction at B left was 3000, so we have this as 300 rather, sorry, then minus 6 in bracket. The reaction at B right, the reaction at B right gave us 675, so we have this as 675, then plus 6 in bracket, the young modulus, which is 3000, times the change at B was minus 0.013. So if we expand this, we are having 6 moment at A plus 6 will give me 12, and 12 times 2 will give me 24 moments at B plus 6 moments at C, which will be equal to minus 6 times 300, then minus 6 times 675, then plus 6 times 3000 times minus 0.013. So my answer here will be, wow, it's a big number, so I'm having 6084. So I can further reduce this. I reduce this part with MB, so I can reduce this as well with moment at B. So reducing this with moment at B, I'm going to be dividing all through by 24. And dividing all through by 24, I'll have that my 6 divided by 24 is going to give us 0.25. This is 0.25 moment at A plus moment at B plus 0.25 moment at C equal to 6084 divided by 24. That will give me minus 253.5. I can call this my equation 2. And then we've generated our equation 1 and likewise our equation 2. So the next thing for me to do here is to generate my equation at support C. To generate my equation at support C. And to generate my equation at support C, I'll have this, that my moment, let's go back to our question again. My moment, I'm generating my equation at support C, so I'll be taking this B, C, and C prime. Remember, the first thing we took was A prime, A, and B. Then I took A, B, and C. Now I am taking B, C, and C prime. And at this, my main purpose is to find my moment at C when I'm taking this last support. So now at support C, we are going to be having this, that our moments, I'm taking this as moments at B. This is support B, C, and C prime. So to generate my formula here, I'll be having that moment at B multiplied by the length of B to C plus 2 times a moment at C multiplied by the length of BC plus the length of C and C prime, then plus the moment at C prime times the length of C to C prime, then which should be equal to minus 6. Since I am at C, I'll be finding the reaction at C left, I naught over I, minus 6 reaction at C right, I naught over I, then plus 6 E I theta C. Before now, we should have known our 3 moment equations, how to generate it, and I am just generating it using the questions here. So because it is called the 3 moment equation, you take it 3 support at a time. 1 2 3, 1 2 3, 1 2 3. So now, substituting inside this support C, I have that my moment at B multiplied by the length of BC. Length of BC was 6 moment at B plus 2 moment at C. The length of B to C is 6, and the length of C, this is 0, and this will be 0. So I'm only having this. This is 0 because the length of C prime was not given to me. So it's 0 times whatever length that is there. That 0 for your length from here to here wasn't given to me. So it's definitely 0. And here, since the length of this to this is 0 multiplied by whatever moment C is carrying, will definitely make it to be 0. So I'm now having this as equal to minus 6. The reaction at C left C left from our question was 675. So I'll substitute this as 675. The reaction at C right, this is the C right, and because it is C right and it is the imaginary part of C, so everything here will turn out to be 0. So this is 0, then plus 6 in bracket multiplied by my EI is still 3000 from our question. Please don't get confused. You can ask any question you want to ask on the comment section and I'll reply to that later. So this is 6 times 3000 times the settlement at C we calculated as minus 0.0083. So expanding this, I'm having 6 moments at B plus 12 moments at C equal to minus 6 times 675, then plus 6 times 3000 times minus 0.0083. So this would give me minus 4199.4. So reducing everything with 6, which is the moment at B, I'm having that my moment at B would plus 12, that is 12 divided by 6 to give me 2 MC, which is equal to 4199.4 divided by 6 would give us equal to minus 699.9. So this is my equation 3. At this point, we're almost done with our calculation because here is where we would need to solve simultaneously. And if I am solving the equation simultaneously, I will have that my first equation was 2 moments at A plus moments at B equal to minus 285. This is my equation 1. And then the next one is 0.25 moments at A plus moments at B plus 0.25 moments at C equal to minus 253.5. And this is my equation 2. Then the equation 3 was moment at B plus 2 moments at C equal to minus 699.9. And this is my equation 3. Now, to solve this simultaneously, I would have to take from equation 3, sorry for the obstruction, from equation 3, our equation 3 gave us our equation 3 was, that is, moments at B plus 2 moments at C, which is equal to minus 699.9. So making my MB subject of the formula, I'm going to be having minus 699.9 minus 2 moments at C. I can call this my equation 4. So this is my equation 4, and substituting actually this can be solved with the help of a calculator, but for reference purposes I'm going to be using my substitution method to solve the simultaneous equation. I'm having a 3 equation. Either you use your matrix method or you can use a substitution or elimination method, whichever one that is better for you. But for me, I normally prefer to use my substitution method when it is more than 2 questions. So substituting equation 4 into I and II. So I'll be having this, that this is 2 moments at A plus minus 699.9 minus 2 moments at C, which is equal to minus 285. Then the next one, I'm having 0.25 moments at A plus moment at B was minus 699.9 minus 2 MC, then plus 0.25 MC, which should be equal to minus 253.5. Then resolving this, Resolving this, I'll have that this is equal to 2 A minus 2 moment at C, then equal to this. I am assuming that I've opened this bracket because this is a plus sign, so it's not going to affect anything that is inside here. So moving this to this other side, I'll have this as minus 285 plus 699.9. So this will be equal to 414.9. So for the next question, I'm having two moments, that is 0.225 moments at A, then minus 2 plus 0.25 will give me minus 1.75 moment at C, then this is equal to minus 253.5. This moving to this other side will turn to positive plus 699.9. So this will give me 446.4. I can call this my equation 5 and this my equation 6. So the next thing I have to do is to make any of them my subject of the formula. I can start from equation 5. From equation 5, I can make my 2A, that is, let me write it out for this is 2 moments at A minus 2 moments at C equal to 414.9. So let me reduce everything by 2. I'm having that, or I can have this, that this is moment at A minus moment at C equal to 414.9 divided by 2 will give me 207.45. So making my moment at A subject of the formula, I'm going to be having this, that this is 207.45 plus MC. I can call this my equation 7. Then the next thing I have to do here is to substitute my equation 7 into equation 6. So substituting equation 7 into 6, I'm going to have this, that this is 0.25 in bracket 207.45 plus MC minus 1.75 MC will be equal to 446.4. So opening this bracket, I'm going to have 0.25 times 207.45 will give me 51.86 plus 0.25 MC minus 1.75 MC equal to 446.4. If you notice very well, at this stage we are now having 2 MC where we can easily find the value of our MC. So 0.25 minus 1.75 will give me minus 1.5 MC would be equal to 446.4. Moving this to the other side of the equation, I'll have it as minus 51.86, and my value would be 394.54. Therefore, I can divide both sides by minus 1.5 such that my MC would be equal to 394.54 divided by 1.5. My value will be minus 263.03 kilonewton per meter. That means that my moment at C is 263.03 kilonewton per meter. So with this, we are close. We can now substitute our MC into equation 7 and into equation 4. So substituting MC into equation 7 and equation 4, I'll have that my MA would be equal to 207.45 plus minus 263.03. So this would give me that is 207.45 minus 263.03. That is equal to minus 55.6 kilonewton meter. Likewise, if I should substitute on equation 4, I'm going to have that my MB will be equal to minus 699.9 minus 2 times minus 263.03. So this should be minus 699.9 minus 2 times minus 263.03, which should give my answer as minus 173.84 kilonewton. Wow! At this stage, we've been able to find that therefore our moment at A was equal to minus 55.6 kilonewton meter. Our moment at B equal to minus 173.84 kilonewton meter, and our moment at C equal to minus 263.03 kilonewton meter. Now, we've been able to find our moments at A, at B, and at C. The next thing we have here is to draw our bending moment diagram. Thank you for watching. I would be drawing our bending moment diagram on our next video. Do it to subscribe and do it to like. If you have any more questions on this, you can ask, and on our next video we'll be able to draw our bending moment diagram and also our shear force. Thank you.